Okay, so today I'm going to start by just doing a couple of problems that are out of the exercises at the end of chapter 1. So I chose exercise 9a. So it says, let G be isomorphic to H. This is the symbol for isomorphism, where one or more vertices in G has degree R. And since G is isomorphic to H, that of course means that H also has vertices of degree R. Let S be the set of vertices in G of degree R, and let T be the set of vertices in H of degree R. Prove that G induced on S is isomorphic to H induced on T. Part of the reason why I'm doing this example is to reinforce this definition. This definition is sort of in between pages 10 and 11 of what it means to have like G bracket a set of vertices. I'm going to show you an example, but if you want to look up the definition of that before I do it, then it's here. Okay, so like I said, I have an example. So here's two graphs. I drew them so that they're pretty clearly isomorphic. The names of the vertices are different, but you know, we have these 5 vertices on the outside that are making like a pentagon, and then one vertex in the middle that's adjacent to all of those, and that describes both of these graphs. We could, and I think I will eventually say explicitly what an isomorphism is between this graph and this graph. But before I do that, let me do something else. Let's say in this example that R is 3. And sure enough, both graphs have vertices of degree 3. All of these on the outside have degree 3. The one in the middle is the only one that doesn't have degree 3. And then that's true of both graphs, of course. So S, the set of vertices in G that have degree R, that would be all of these. It's every vertex except for Z. So this is S. It's all the vertices of degree 3 in G. T is supposed to be all the vertices of degree 3 in H. So 1, 2, 3, 4, 5. Okay. And now let me draw G induced on S. Here's how you draw this. This is going to be a graph. It's going to be a subgraph of G. It's only going to have the vertices in S, though. So the vertex Z is going to be missing. So I'm going to start by just drawing all the vertices. And I'm going to arrange them the way they're arranged above, because that'll make things easier visually. And G induced on S, basically any edges that have both endpoints among these vertices is going to be included. So there's an edge with an endpoint V and an endpoint W. So those are the two endpoints of the edge, and those are here and here, so I'm going to draw that edge. There's an edge from W to X. There's an edge from X to Y, Y to U, and U to V. And we have all of those. Of course, we're not going to have any edge that was touching Z, because Z is not in this picture anywhere. And that's it. We don't have any edge touching Z, but we have everything, every other edge. That's G induced on S. Okay, and we're supposed to show that that's isomorphic to H induced on T. So what's H induced on T? Once again, it has these 5 vertices. 1, 2, 3, 4, 5. And I'm just going ahead and drawing the edges. I'm doing it faster than I did before. So I get this. And we're supposed to, or the example, or the problem is for us to show that these are isomorphic, not just for this specific example, but for any graphs. I'm just illustrating it with this example. In this example, they're clearly isomorphic. Like this graph is clearly the same as this graph. It's just the names of the vertices are different. So yeah, before I get into the general proof, let's talk about an explicit isomorphism from G to H. So maybe my isomorphism will be called F, and we've done explicit isomorphisms before, where I just have to tell you what is F of each vertex. So there's 6 vertices here, and maybe I'll go in order. U, V, W, X, Y, Z. And these values on the right, they're going to be vertices in here. And so what is the correspondence between these two graphs? Basically, of course, Z corresponds to the vertex 6. That's the vertex that's in the middle. And then going around, like these ones correspond to these ones. So why don't I say that f of z is 6? And then why don't I say that, well, maybe it makes the most sense to go in alphabetical order. U, V, W, X, Y will be 1, 2, 3, 4, 5. And I have some choices here. U doesn't have to go to 1. I could sort of start anywhere here and go around, but maybe it makes the most sense to say that f of u will be 1, f of v will be 2, 3, 4, 5, 6. And I guess the reason why I'm doing that is if I just, okay. So this is an isomorphism between the two original graphs, and what we're supposed to show is that these two new graphs are also isomorphic. What I'm basically telling you is that if I look at this isomorphism and I just ignore the vertex that doesn't appear down there, right? The vertex Z doesn't appear down here, and the vertex 6 doesn't appear over here. And f of z was 6, which is convenient, because if I just cover this up with my finger, what's left is telling me an isomorphism between this graph and this graph. F of u is 1. So it's like as I go around this cycle, I'm going u, v, w, x, y, and that corresponds to 1, 2, 3, 4, 5. So this is an isomorphism between these two. So, right, I did that example to kind of illustrate what the general solution is going to be, which is, so once again, we're assuming that G is isomorphic to H, and I want to, yeah, we have this number R, and S is the vertices in G of degree R, and T is the vertices of H of degree R, and I have to show that G induced on S is isomorphic to H induced on T. So suppose we have our isomorphism, because we're assuming that G is isomorphic to H. So let F be an isomorphism, and we know that there is one. And basically what I want to argue is that the thing that we just saw in the example is always true. In other words, if I look at the isomorphism from G to H, that function is basically already telling me an isomorphism between G induced on S and H induced on T. So here's what I'm saying. Suppose little s is one of the vertices in big S. Then where can the isomorphism send little s? In other words, what's f of little s? Well, this is the set of vertices of degree r in the graph G. So little s is a vertex of degree r. That means that in an isomorphism, f of little s would have to be a vertex that has degree r in H. In other words, this would have to be in the set T. Right? I mean, if f is an isomorphism, then the degree of a vertex has to be the same as the degree of the image of that vertex under the isomorphism. Similarly, if I take a vertex in T, so that's a vertex that has degree r in H, and I look at f inverse of T, that would have to be in S. And again, that's because little t has degree r, so its inverse image would have to have degree r because this is an isomorphism. So what that means in other words, f is an isomorphism. From G induced on S to H induced on T. So yeah, that's it. Let's say we do another exercise. This one's about the two switches. If you remember, two switches were these operations that basically you go from this to this. So you've got four vertices, these two edges are there, these two edges are not there. These cross edges may or may not be there. It doesn't matter. But what you do for this operation is you remove these two edges and then you replace them with these two edges and you get this picture. And the reason why we talked about two switches is because it's possible to get in between any two graphs that have the same degree sequence using a sequence of two switches. So here we have two graphs that have the same degree sequence, right? The degree sequence is 3, 3, 2, 2, 2. Each of these graphs has two vertices of degree 3 and three vertices of degree 2. These aren't the same graph. They're not even isomorphic. This graph has a triangle in it. It has three vertices that are all adjacent to each other, and this graph does not. However, it's possible to get from one graph to the other using a sequence of two switches. So let's try to be smart about this. I don't want to just randomly start doing two switches and see what happens. What is different about these two graphs? One thing that's different, even though they have the same degree sequence, In this one, my two vertices of degree 3, they're adjacent to each other. I've got this one, and there's this edge making them adjacent. In this graph over here, I have my two vertices of degree 3, and they are not adjacent to each other. So that's something that I can focus on and maybe give myself some direction here. I would like to, say, take this graph and apply a 2-switch so that it's more like this graph. And what I'm going to focus on is the fact that these degree 3 vertices are adjacent to each other, but I don't want them to be. So I would like to do a 2-switch that gets rid of this edge. So what can I do here? I can let's see. I'd like to get rid of this edge. So why don't I focus on these 4 vertices? Now, you might look at these 4 vertices and say you can't do a 2-switch on those, because a 2-switch looks like this. You have this edge, you have this edge, but it's important that you don't have this edge and that you don't have this edge. And I just circled these 4 vertices, and well, I have this and this, but then I'm not supposed to have this, and I'm not supposed to have this. However, that's not thinking about this, I don't know what the word is, maybe creatively enough. Or maybe creatively isn't the right word, but let me point something out. I don't have this edge, and I don't have this edge. So it's like if, maybe I'll give names to these vertices, like if this is A, B, C, and D, then I can call this A, B, and then instead of this one being C and D, I'll write C will be this one and D will be this one. And let's look at this again. I have the edge from A to B, which is what I'm supposed to have. I also have the edge from C to D, and I'm supposed to have that as well. Now let's look at the edges that I'm not supposed to have. I'm not supposed to have an edge from A to C, and look, I don't. And I'm not supposed to have an edge from B to D, and look, I don't. So this I can do, this is a valid 2-switch. And what would that do if I made that 2-switch? That would mean the edge AB is now no longer there. The edge from C to D is no longer there. And then now this one is there and this one is there. And all of the other edges that were there are still there. So this one, this one, this one, and this one. And let's take a look again. Now I've got my 2 vertices of degree 3 and my 3 vertices of degree 2, and the degree 3s are not adjacent to each other, and I don't see any degree 2s that are adjacent to each other. So I think that means that this and this are basically the same graph. How can we be sure of that? Let me label the vertices, and maybe I'll label them like 1, 2, 3, 4, 5. So 1 and 2 will be my degree 3s. 3, 4, 5 will be my degree 2's. And we can check all of the edges, like 1 is adjacent to 3, 4, and 5. So 1 is adjacent to 3, 4, and 5. 2 is also adjacent to 3, 4, and 5. So 2 is adjacent to 3, 4, and 5. So yeah, you can check that everything that's supposed to be adjacent to something else actually is. And so this and this are just two different drawings of the same graph. So actually, the direction said find a sequence of 2 switches. We managed to do it in just a single 2 switch, and that's fine. So I started with G, I applied this 1, 2 switch, and I got this, which turns out to be the same graph as H. Okay, so I think I have time still. I can't make these videos too long or else it gets cut off, but I think I have time. So I'm just going to start talking about the beginning of chapter 2. So for right now, I'd say it's not strictly necessary that you read any part of chapter 2 before you watch this part of the video. It'll be pretty self-contained. So don't worry about that. I'll have you read chapter 2 later. So, all right, here we go. A walk in a graph is a sequence of vertices. And we write a sequence this way in parentheses. So it starts with V naught and ends in VK, such that VI and VI plus 1 are adjacent. For each relevant value of I. The length of the walk is K. Keep in mind that this starts at 0, so there's actually K plus 1 vertices. We say that the length is K, though. And if U is the starting vertex and V is the ending vertex, we call this a UV walk. And then there's some special kinds of walks. A trail is a walk that doesn't repeat any edges. So what do I mean by that? Of course, consecutive vertices are supposed to be adjacent. So V naught is adjacent to V1, V1 is adjacent to V2, and so on. And so there's these edges. There's the edge from V naught to V1, the edge from V1 to V2, and so on. A trail doesn't use the same edge twice. A path is a walk that doesn't repeat any vertices. So let's take a look at a graph and some sequences of vertices and talk about whether they're walks or trails or paths. So the first one, to check whether it's a walk, we just have to check that consecutive vertices are adjacent. So 1 is supposed to be adjacent to 2. Okay, it is. 2 is supposed to be adjacent to 3. Okay, it is. 3 is supposed to be adjacent to 1. Oh no. So no, it is not a walk. That means it can't possibly be a trail or a path. Trails and paths are just kinds of walks. So if it's not even a walk, then it has to be no all the way across. So that's how we can check whether something is a walk. For the rest of these, they're all going to at least be walks. Some of them may be trails or paths or not. So let's take a look at the next one. And we can check real quick that it's a walk. I'm going to stop checking this in a second. But 2, 3, 4, 1, 2, 3. Now, all I'm checking is that I'm going along edges every time. So 2, 3, I see this as an edge. 3, 4, I see this as an edge. 4, 1, I see this as an edge. 1, 2, I see this as an edge. And 2, 3, I see. Okay. Is it a trail? Well, I used the edge from 2 to 3. That's what I do first. And then I go 3 to 4 to 1 to 2 to 3 again. So I use this edge twice, right? I go from 2 to 3, and then I go from 2 to 3. So this is not a trail. And it's not a path just because, I mean, I see like a 2 and a 2, a 3 and a 3. On a path, I'm only allowed to use each vertex once, so it's definitely not a path. All right, let's take a look at this one. You can check that it's a walk. That's easy enough. I trust you to do that. Is it a trail? I go from 2 to 3 to 4 to 1, back to 4, and then already I'm in trouble, right? I went from 4 to 1 to 4. So that's going here, using this edge, and then using the same edge again. And this is something you have to be careful of, like using the same edge in the opposite direction. Like I went from 4 to 1, and then I went from 1 to 4, but that counts as using the same edge. By the way, there's another reason why this isn't a trail. Because it goes from 2 to 3, and then at the very end it goes from 3 to 2. So it would be using this edge twice. So there's a couple of reasons why this isn't a trail. And of course it's not a path because I see multiple copies of 2 and multiple copies of 3. I see multiple copies of 4, so whoops, no. Okay, next one. It is a walk. You can check that yourself. Is it a trail? 4, 3, 2, 4, 1, 2. I don't think I used the same edge twice. And if you're, of course you can check this. So I go 4, 3, 2, back to 4, and then 1, and then 2. I didn't find myself tracing over the same edge twice. So I would say, yes, this is a trail. It's not a path because this involves the vertex 4 multiple times and the vertex 2 multiple times. This one is a walk. It is also a trail, and it is a path. This one goes 1, 5, 3, 4, 2. It doesn't even repeat vertices. By the way, all paths are trails. Let me say that another way. If something's not a trail, then it's definitely not a path, because if it's not a trail, according to the definition, that means that it repeats an edge. If you're going to repeat an edge, you have to repeat the vertices that are on that edge, in which case you can't be a path. So if something isn't a trail, then it's not a path. In other words, if it is a path, then it is a trail. All right, and I just want to state a theorem. This is basically Theorem 2.1. This is a slightly weaker version than what is in the book, but I'm going to say that this is basically Theorem 2.1. So here's the theorem that I'm going to state. Let U and V be vertices in a graph G. If there's a UV walk in G, then there's a UV path in G. So let's talk about what this means. This is what we're talking about now is kind of using graph theory to represent it's like representing the ability to travel between different places. The vertices of a graph are different places you can go to, and the edges of the graph are ways to get from one place to another. And when we talk about a walk, it's like talking about this sequence of vertices where I can get from this vertex to that vertex because there's an edge to travel along, and then I can get from that vertex to the next vertex because there's an edge to travel along. So we're kind of imagining ourselves traveling along the edges from vertex to vertex. So if there's a UV walk in G, that basically just means that there's a way to get from U to V by starting at U and traveling along an edge and then maybe another edge and then another edge until you get to V. And what this is saying is if you have that, then there's a UV path. In other words, there's a way to get from U to V that doesn't visit the same place multiple times, because a path doesn't use the same vertex multiple times. So here's a picture. Suppose that there's a walk from U to V, so there's some sequence of vertices like this. Of course, I didn't draw a very efficient walk because this, well, it kind of loops around and it visits the same place twice. Like it visits this vertex twice. Like when I say it visits, I mean as I travel along, I'm going through this vertex twice. So the point is, if we have such a thing, then it's possible to get from U to V without visiting the same vertex twice. And I can, and in this picture at least, I can show you how. I would just go here, and then instead of looping around, I would just keep going here. That's a path. This vertex is adjacent to this vertex, is adjacent to this vertex. I can get from here to here. I can get from here to here without going around. I can just get from here to here directly. So, right, it's like walks are, if a walk is visiting the same vertex more than once, then in some sense you could say it's not an efficient walk. It's longer than it needs to be. So, and that's going to hint at the proof here. So let me run through the proof. We're supposing, once again, that there's a UV walk in G. So let's give it a name. Let W be the UV walk. So it's a sequence of vertices starting at V0 and ending at VK. U is the beginning vertex, so I wrote U equals V0, and V is the ending vertex. That's why I wrote V equals VK. So let that be our UV walk. And since we believe that the short walks are the ones we should be looking at, because a path is like an efficient walk. It's like going directly there without visiting the same place more than once. So paths are shorter than walks in general, or whenever you have a walk that isn't a path, you can find one that's shorter. Therefore, we're going to think about it, we're going to consider a walk of minimum possible length. And then we're going to argue that that is a path. So then this is going to be by contradiction. Suppose that W has a repeated vertex. In other words, there's some VI that equals VJ. Remember that formally this walk is a sequence of vertices, and we're saying that there's the same vertex that appears twice on this list. So maybe VI is the same vertex as VJ for some I and J that are different. We can assume I is less than J. But then, just as we had up in this picture, I can give you a shorter walk. The shorter walk would just start at V0, and then it would go to V1, and it would follow the same pattern of vertices up until you hit VI, And then keep in mind that VI is the same vertex as VJ. So like in this picture, this vertex is playing the role of VI and VJ. So you would go up until you hit VI, and that's the same vertex as VJ, and then you would follow the rest of the walk that you're supposed to follow after VJ. In other words, you go directly to VJ plus 1, VJ plus 2, up until you hit VK. And so you cut out all of the vertices that would, or you cut out all of the vertices that would be in between VI and VJ. And so what we've done is we've gotten a shorter walk. But that's a contradiction because we assumed that W was the shortest UV walk. So that's a contradiction to our assumption that W had a repeated vertex. In other words, W can't possibly have a repeated vertex. In other words, W is a path. So there is a UV path in G. Okay, so maybe I'll leave this lecture there.